wild-looking airplanes. This is the extreme of post-war design as far as anything that has actually gotten onto a race course. And the speaker will be Michael Schratt from Crystal Lake, Illinois. He works as a, and I will read this because I don't know what it means, 3D solid model CAD drafter in the aerospace industry. I know what the aerospace industry is. And in addition to his presentation, he has written and illustrated a booklet on the life of the pond racer. And he's a private pilot with power and glider ratings. So, Michael, where are you? Oh, I'm afraid he'd escaped. Come on up.
No.
Well, first of all, I want to thank Don for giving me the opportunity to join all of you today. And what I'd like to do for you is give you a brief overview of the design, construction, and test flight program of the Pond Racer. And we've got a lot of material to go through, so I want to go ahead and get started. And I thought it was appropriate that we begin with a few comments made by Dick Rattan, one of only 3 test pilots that ever actually flew the Pond Racer. And here we see Dick says, in order to determine what your limitations are, you occasionally need to exceed them. And then he went on to say, when technology has sufficiently progressed to a very advanced state, it's indistinguishable from magic. And we're going to talk about a little bit of magic technology as we go on here. Design philosophy of the Pond Racer was number 1, to design, build, and fly the fastest reciprocating piston-powered aircraft and set new absolute and time-to-climb speed records. That was the first goal. Number 2, compete at the Reno National Air Races and beat the heavy iron, which includes the Mustangs, the Corsairs, the Sea Furies, thereby saving an important part of our national history. And number 3, utilize trickle-down technology developed from the Pond Racer program for use in the private sector and general aviation, which includes more efficient airframes, propellers, and advanced engines. So these are the 3 design key goals of the Pond Racer program. The 4 key players in Pond Racer was, of course, Bob Pond, which is unfortunately no longer with us now. Dick Rattan headed up the test flight program. John Knepp of Electromotive headed up the engine development program. And Bruce Evans down here was a crew chief for the Pond Racer program. Diminishing returns and drag coefficients. This is something very significant to discuss here. Look what's happening in unlimiteds today. They triple the power and only get 2% more speed. That ought to be telling somebody that they're working on the wrong end of this push-pull thing. Dick Rattan, highlighting a very important point on what we're going to discuss here. How fast can I go? There's a mathematical equation that goes like this. Drag goes up by the square of the airspeed, and the horsepower requirement to overcome that drag goes up by the cube root of the velocity. So that means that if you have a brand new racing aircraft, you have 100 horsepower, you're going 100 miles an hour, you're going to need 800 horsepower to go 200 miles an hour using the existing airframe. Now, due to a number of factors, including induced drag, those real-world numbers and horsepower values are slightly less than that. But it just goes to show you here that adding more horsepower to the aircraft is not going to make the aircraft go faster. You're eventually going to reach a theoretical limit where adding more horsepower is almost useless. Key elements in racing aircraft design: aerodynamic drag, engine performance, propeller efficiency, and weight. And a couple things here for aerodynamic drag. We'll break this down quickly. That's the profile drag, or the frontal area or cross-section, which was a key element in the tsunami. The steam friction drag, or laminar flow composite materials. That's how we acquire that. Induced drag is drag related to lift. Transonic shock waves, compressibility, that's dealt with swept wings and area ruling. Intersection drag, P-38 had a lot of intersection drag. Drag associated with heat, waste, or cooling drag. Modified exit ramp is some way you can take care of that. Low profile air scoop, glassing the wings, reduced tail area, cut down the canopy. These are all elements in a new racing design. The removal of flaps, that's another thing you can do to bring the drag coefficient down. Plug all the air holes, vertical tail offset, modified wingtips, horizontal tail adjustment, wing fairing, and clip wings. All these things contribute to an aerodynamically efficient racing aircraft. Now, when it talks about vintage performance and aircraft engines available, we really don't have a lot available. If you really look at what's out there, here's your choices. You have the Orenda 600, which never went into production in any great numbers. You have the turbo diesel series that doesn't have enough horsepower. You need at least 2,000 horsepower to be competitive at Reno. You have the Merlin and Griffin series of Rolls-Royce engines. And you also have the Pratt & Whitney R series or radial engines. Those are really the choices here, and this is what we just talked about here. Of course, we have the Michael Zucca turbo diesel, and I want to talk about that. What you can do to increase your engine performance is the increased oiling, the high compression pistons, optimized blower gear ratios, larger exhaust stacks, nitrous injection, aftercooler, ADI, anti-friction coating, and steam afterburner, which we're going to talk about in a little bit later here. Propeller efficiency. What you can do with propeller efficiency is the twin contra-rotating blades, the multiple swept blade, or the NASA unducted fan technology that was used in the 1980s. Propeller tips must be kept below supersonic to maximize efficiency, and that's extremely important. Weight associated with induced drag. That is dealt with by a carbon fiber aircraft construction, a smaller aircraft, and lighter weight achieved by lightweight modern engines taking place within Relentless NXT. Now, a brief historical overview here. Red Baron RB-51, the power plant was a Rolls-Royce Griffin V12. Horsepower was 2,500 horsepower. Under the racing condition, it produced much more than that. Top speed was 499.018 miles per hour. That was set on August 14, 1979, with Steve Hinton as the pilot. And unfortunately, just after that, during Reno 1977, there was a significant problem in the engine. The props went to flat pitch. He crashed, but eventually went on to race again. Extensive modifications done by Pete Law and Bruce Bolin on Red Baron include the clip wings, the taller tail, a low-profile canopy, a totally new fire-forward package, engine induction system, radiator, oil cooler, spray bars, and ADI, and Pete Law is really the world's foremost person when you want to do that to your aircraft, and nitrous injection. Tsunami, wingspan 27 feet 6 inches, length was 28 feet 6 inches, power plant was a Rolls-Royce Merlin, horsepower was 2,400. Originally was designed to have a single-stage blower, but when Dreadnought came on the scene, they upped that to a full race-bred engine. Top speed was approximately 500 plus. So really, the Tsunami Air Racer was an experiment on the smallest airframe that could be wrapped around a Merlin engine. That was the concept behind Tsunami. Bruce Bolin was a senior project design engineer on that program. Half the frontal area of a Bearcat. The most significant factor of Tsunami is the fact that it had half the frontal area of a Bearcat. Flown by Skip Holmes, Steve Hinton at Reno. Miss Ashley 2 is what I'm terming a Franken racer. Essentially,